switch, and we have this escape mechanism. Okay? So I'm not going to say any more about that. That is the release mechanism. Okay? So switching here is due to the escape mechanism, the one I showed you. You can make a very simple model if you replace this Boltzmann function by just a Heaviside function, a switch on and off. Then the model has constant coefficients, except when there's a switch. So you can solve it analytically. You don't know the period of the switch, but you can figure that out. Because the slow variable is slowly changing, all you have to do is figure out when the net input gets to a threshold. So that's schematized right here. There's a threshold theta, and there's the net input. Okay? In the small input case where we have release, okay, the dominant population has as its input the sensory input and the adaptation. The other population has the sensory input, its adaptation, and the inhibition. Okay? So this level is way down here, this level is up here, this is closer to the threshold. This one's decreasing, this one's rising. It's going to get to threshold before this one because it's closer. That's the release mechanism. Okay? The escape mechanism is both of these things get pushed up more because I is bigger. It's on the right branch. So now this bar is closer to threshold than this bar. This one is going to drift upward before this one drifts down. That's the escape mechanism. So sometimes these simple models are very useful to use, a very reduced model. Okay. Okay, so now we could add noise to this perfect oscillator model. Okay, so we did that with an Ornstein-Uhlenbeck process. Just added noise to the net input. Okay, had a certain time scale. Time scale was a little bit slower than the fast time scale of recruitment, which was 1 in this particular case, but much faster than the adaptation time scale. Okay, so that led to random alternations. Okay, and the distribution of dominance durations looks log normal-like or gamma-like. Okay, and now even in the winner-take-all regime, okay, which would look like this without noise, you get alternation. So this is an example of a noise-driven oscillation, a noise-driven alternation. No noise, no alternation in this parameter regime. Okay, still has this undesirable symmetry to it. You get rid of that. Well, part of the reason is I said this Boltzmann function is very symmetrical. The foot and the maxima, the saturation are. If you change the shape of that, you can change the shape of this distribution here. What's the reason for changing that? Well, it's too crude a model to be talking about in that way. Okay, so we have an oscillator model with noise. Okay, no noise, it can oscillate in some parameter regimes. Ruben Moreno was given the task of using a different framework. Okay, and let's come up based on having an attractor model with noise in it. Okay, so Ruben, physicist, said I'm going to start with a double well potential. Okay, and I'm going to add a little bit of weak adaptation. So these wells move up and down a little bit and slowly. And now I'm going to put noise between these two. Okay. If there is no slow adaptation, okay, then you just jump between the two wells. And the rate of that jumping is given by Kramer's law. Okay? It's an exponential distribution. It's not a gamma distribution, it's Poisson. It's an exponential distribution. If you add some slow adaptation, you change this and it becomes looking more like the shifted gamma distribution. Okay. Okay, so Rubin made a double well potential model, okay, and it satisfies this Lavelle proposition 1. This is basically a one variable model. It's the distance between the two wells, right, where you are between the two wells. It's one variable. So he made up a two variable model, so now you're living on a plane. There's two potential wells in this plane. It's a two variable model. If you add a little bit of adaptation, it becomes a four variable model, okay, for the firing rates. And the form of the potential function that he came up with, he tried to interpret in neural terms. I'm not going to drag you through that. You can look at our paper, okay, it's in the appendix, but the form of what he was looking at suggested to him that the two populations, the two units, each had a subpopulation of excitatory cells and inhibitory cells. So the inhibition was local, okay, but there was some global pool that was collecting the activity of the excitatory population and feeding them back to local inhibition. This is a very more or less standard way of also doing winner-take-all dynamics, okay? Feeding the population, the firing rates of all the competing units to some global thing that then feeds back to everybody, okay? So it's not too surprising, but the form of his interactions here had some nonlinearities which are not in the usual description. And that led him to getting a 2D model, okay, for a firing rate description that still satisfied Lavelle's proposition 1. The nonlinearities that he introduced here from his description led to enough asymmetry so that you got rid of that undesirable branch. Okay. And if there's no adaptation, it has exponential looking distributions. And with weak adaptation, it's shifted over. So the adaptation timescale has to do with that shifting. If it's very strong adaptation, it starts to look like an oscillator-based model. If it's very strong adaptation, it can overcome inhibition, overcome the sensory drive, and cause a switch. Okay. Okay, so the architecture of these two models, or this is what I showed you for the simple CPG-like model. In Rubin's case, recurrent excitation played a role. Okay, that changed the basic structure of the response diagram to make it look bistable even for identical inputs. Okay, this is what recurrent excitation can do for you. Recurrent excitation can cause the system to stay like this. Okay, once you recruit enough activity, it's going to stay up. Okay, so that was his contribution. What time did I start? Does anybody know? This doesn't happen very often. Okay. I started okay, I have 15 minutes. Okay. So Rubin also made a cell-based model of this architecture using leaky integrate and fire units for individual neurons, 100 units in each population. Okay. And there was examples where he had intrinsic noise in this. But in some cases, you didn't even need the noise because it was sparse coupling and just the finite size effects would be enough to cause fluctuations to create the alternations. Okay, so here you see the alternations. These are the plots of each